Welcome back, Physical Science 20. So we looked at this, looking at calculating the electric field strength by looking at what happens to a little charge in that area. All right. Now we'll look at the opposite. So we'll look at the electric field made by a certain charge. So we're looking at, we know what the charge is that's making the electric field. What is the electric field going to be a certain distance away from it? So it says here, calculate the magnitude and direction of electric field at a point which is 30 centimeters to the right of big Q. So we're looking at what happens to this. What is the E at point P when I have this electric field being made by a charge, called it Q? Now I know, see this right here? We know that it's a negative charge because we have a negative in front of it. All right, so a couple of things here. So since this point P is to the right, and I know that Q is a negative charge, to figure out what direction the electric field would be at point P, all I have to do is figure out what would happen if I put a positive charge right here. Would it be attracted to the Q or repelled from Q? And since Q is negative, it's going to be attracted. So I know right off the bat that the electric field is to the left at point P. To the left at point P, since it's a negative charge making the field. And of course, we always want to determine the direction. We use a positive charge. What is the effect of the positive charge at that area? So if I'm looking over here, a positive charge is attracted to big Q, so the electric field lies to the left at point P. All right? So if I want to figure that out now, I want to know what's 30 centimeters. 30 centimeters, of course, is 0.30 meter sticks, because we have to have meter sticks, right? E equals KQ over R squared. So the charge, I use a big Q compared to a little q here. The little q, I assume, is a little charge that's experiencing a force, whereas the big Q is the thing that's making the electric field, which can manipulate little q's. So 9 times 10 to the 9, of course, is little k. The charge that's making it, don't even worry about the negative. The negative just helps us figure out the direction of the field after. And then the radius, so we get 310,000, or 3.1 times 10 to the 5 newtons per coulomb. Okay, so you can see the two scenarios here. The two scenarios that are happening. Again, I use this relationship if I'm going to figure out what's happening to a little charge. What force does it experience for that little charge out in an area? That is the result of a larger charge making the electric field. So think of it as Earth and a small object. Whereas here, it's like, oh, I'm figuring out the field strength of the Earth, the thing that's making the field that a box or a spaceship is experiencing. You could kind of think of it like that. Okay, so with that, we've been jumped in and just simply, we have been drawing these kind of like lines of force already. So this should be fairly straightforward. Since the electric field is a vector, it is sometimes referred to as a vector field. We could indicate the electric field with arrows at various points in a given situation, such as A, B, and C that we saw earlier. The directions of EA, EB, and EC, so the electric field. So again, if A is experiencing a northward force, and I know that Q is positive, this of course is a positive test charge that represents the directions. However, the relative lengths of EA, EB, and EC are the same as for forces, since we divide by Q each time. So we can see the further we get out, the less force we experience. To indicate the electric field in such a way at many points, however, would be way too many arrows, which could quickly become cluttered and confusing. To use this, we use another technique called field lines. To visualize the electric field, we draw a series of lines to indicate the direction of the electric field at various points in space. These electric field lines, or lines of force, are drawn to indicate, again, what would happen to a positive test charge. The lines of force due to a single isolated positive charge and for a single isolated negative charge are shown in the figure on the right. So if I have a positive object, what would happen if I put a positive small charge there? Well, it would be repelled. So the lines of force that are around a big positive charge are going away from it. Whereas over here, a positive charge would be attracted to a negative charge. So if the charge that's making the electric field is negative, the lines of force point towards it because they indicate what would happen to a positive charge if it was nearby. So with the positive charge, the lines point radially outward from the charge, and with negative, they point towards it because it's the opposite direction. Only a few representative lines are shown. We could draw lines in between those lines since the electric fields exist there as well. We could draw the lines so that the number of lines starting on a positive charge or ending on a negative is proportional to how big it is. Notice that near the charge, the electric fields are greater. So if you look over here, the distance between these two lines is really small, whereas when I go out here, the distance is bigger. So the closer you get, the stronger the electric field is over there. This is the general property of electric fields. The closer the lines are together, the stronger they are. In fact, field lines can be drawn so that the number of lines crossing unit per area is proportional to the magnitude of the electric field. The figure on the right shows electric field lines due to two equal charges of opposite sign, a combination known as an electric dipole. So if I have a positive and a negative, we go away from positive. We go towards negative. And then, of course, these field lines can intersect with one another, away from positive and towards negative. So you can see they get kind of, they combine with each other because we have this, right, with the positive charge, away towards, away towards, away towards. So they kind of intersect with each other and combine into making one big loop from one to another. A few other examples on the next page. Curved in this case and directed from positive to negative. The direction of electric field at any point is tangent to the field line at that point. If we have two equal charges, away from positive, and they don't line up. So they repel each other and make kind of this curved shape away. So, and then the same thing would be true for two negatives, towards negative, towards negative, towards negative. Now they wouldn't combine here, they would be separate. So you're going to get a curving. The picture looks very much the same as here, except the arrows are opposite. So we have that. And below here we have something that has a negative and positive, and this one has twice the charge as this. So we could take a look here, 1, 2, 3, 4, 5, 6 lines here versus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, close to 12 there, being double. So we have double the lines here because it's twice the charge. But again, you can see there's a combining here, away from positive, towards negative. So you have an overlap there. Finally, the figure below, we see a cross-section of the field lines between two flat plates. Notice that the electric field lines between the two plates starts out perpendicular and goes directly from one plate to another, as we expect, because positive test charge placed between these two plates would want to go to the right, towards it's attracted to the negative. Over here at the ends, we could even say, away from positive towards negative. Away from positive towards negative. So it curves outwards at the edges and again continues the path towards the negative over here. So away from positive towards negative. So on the last page here, the fringing of the field near the edges can often be ignored, particularly if the separation of the plates is small compared to their height and width. So properties of electric fields here in summary. Electric field lines indicate the direction of the electric field. The field points in the direction tangent to the field at any point. And then lines are drawn so that the magnitude or size of the field is proportional to the number of lines you see. So the closer the lines together, the stronger the field. Or the more lines you see, the stronger the field. And electric fields start on the positive and end on the negative. And the number starting and ending, again, is proportional to how big it is. Also note the field lines never cross, because it would not make sense for an electric field to have two directions at the same point. All right, so you should be able to do the assignment for that, ladies and gentlemen. and we'll see you again.